Now that we've got our definition in place, our definition of a derivative, we're going to start doing a lot of the same things that we did when we talk about limits, for example. How can we do this more easily? Because the definition is nice, but it's not always easy to use. So the first thing we want to do is we want to generalize the derivative a little bit. Instead of talking about the derivative at an individual point, I want to think of the derivative as a function that we literally derive from the original one. So instead of being a number, the derivative is now going to have a variable in it. And the idea here is if you want to know the derivative at a certain point, you just evaluate f prime of x at that point. All right, so what I've got here on the left side, this is just our existing definitions, right? Our existing definition of the derivative. And you see what I did on the first one? All I did is I replaced the a's with x's. Now I'm going to, when I let h go to 0, remember what that means. It means all of the h's get replaced with 0. So the h's are going to go away, and all that will be left will be x's. Now it gets a little trickier for the second one because the second one already has x's in it, right? But you see what I've done here is they've kind of switched position. The a's all became x's, and I didn't want to reuse a, right? So I used another variable. I put b in here, and then I'm going to let b approach x. So remember what that means. In the end, I'm going to take every b in the formula and replace it with an x. So the b's will have gone away, and I'll be left with an expression that just has x's in it. And those will be my formulas, my functional derivatives. All right, so let's see how this works. All right, so I've got this function f of x equals 3x squared plus x. And I want to use it to find the instantaneous rate of change of f at 4. Okay, but I want to use my new method, right? I want to try to come up with a formula, and then I'll evaluate the formula at 4 and see what we get. So my new definition says f prime of x is the limit h approaches 0, f of x plus h minus f of x over h. All right, so let's see. The limit is going to be here for a while. Don't forget to keep writing the limit. I know we're not going to, that part isn't going to go away. We're not going to evaluate the limit for 3 or 4 more lines yet, but don't lose track of it because I've seen this happen. Students stop writing that limit because they get so focused on the parts that's changing. And then when they get to the end, they forgot about the limit so long ago, they've forgotten that it's a limit that they're taking, and they think they're done when they really aren't. So don't forget to keep writing it. So f of x plus h is 3 times x plus h squared plus x plus h minus 3x squared plus x all over h. This is the limit h approaches 0, 3x squared plus 6xh plus h squared plus x plus h minus 3x squared minus x all over h. Now, everything without an h in the numerator should cancel out. I've got 3x squared minus 3x squared, and I've got x minus x. And that leaves me with the limit h approaches 0, 6xh plus h squared plus h all over h. And let's see, factor an h out of the numerator. If you factor an h out, this becomes h times 6x plus h plus 1. And then the h in the denominator will cancel. And what's left is the limit h approaches 0, 6x plus h plus 1. And if we substitute 0 in there for the only h, all that's left is 6x plus 1. So now let me write the original back in. F prime of x equals 6x plus 1. And now I can do this over and over again. If I want to know the rate of change, the instantaneous rate of change of at 4, f prime of 4 is 6 times 4 plus 1. That's 25. Could have done 3, could have done 0, could have done -4. All just as easily. I can crank out these instantaneous rates of change now for any x value I want really quickly. All right, so let me give you one. Try working this one out, see what you come up with. All right, so let's see. I'm going to use my definition here. F prime of x is the limit h approaches 0, f of x plus h minus f of x over h. Whoops, that made a mess. Sorry about that. So let's see. This is the limit h approaches 0 to x plus h squared plus x plus h minus 3 minus 2x squared plus x minus 3 all over h. All right, so now just a lot of algebra here, right? Multiplying everything out. Limit h approaches 0, 2x squared plus 4xh plus h squared plus x plus h minus 3 minus 2x squared minus x plus 3 all over h. Now, lots of stuff should cancel. 2x squared minus 2x squared, that's 0. X minus x, and minus 3 plus 3. Excellent. Let's see what's left. Limit h approaches 0, 4xh plus h squared plus h all over h. And that numerator, that's going to factor. I can bring an h out. H times 4x plus h plus 1. Now the h's cancel. And I'm left with the limit h approaches 0, 4x plus h plus 1. And if you replace the h with 0, the derivative of this function is 4x plus 1. So f prime of 0 is just 4 times 0 plus 1, which is 1. And that's it. There's my instantaneous rate of change. Okay, so how about this thing? This time I want to actually find the equation of the tangent line at 1. All right, well, let's see if we can use our new method here, right? We'll keep applying this. F prime of x is the limit h approaches 0. You're going to get tired of writing this after a while. F of x plus h minus f of x over h. It's actually good practice when you're learning it. It helps to really strengthen that memory in your mind. So this is the limit h approaches 0, 1 over x plus h minus 1 over x all over h. Now I got to combine these fractions together. I'm going to do that with a common denominator. This will be the limit as h approaches 0, x over x times x plus h minus x plus h over x times x plus h, still over h. All right, now I can combine them together. This is the limit h approaches 0, x minus x plus h over x times x plus h times 1 over h. All right, so good things are about to happen up on top. This is the limit h approaches 0. This is x minus h. Still over that common denominator times 1 over h. All right, x minus x, that's 0. Now this h in the denominator cancels with the h up here in the numerator, and I get the limit h approaches 0, -1 over x times x plus h. And now I can do the limit part. Substitute 0 for h. This is negative 1 over x times x plus 0. So that's negative 1 over x squared. Now I can get on with the finding the equation of the line. This is, we've been calling it the instantaneous rate of change throughout this lecture, but remember, it is also the slope of the tangent line. So the slope at x equals 1 is f prime of 1, which is negative 1 over 1 squared, which is negative 1. And let's see, what else do I need? I'm trying to find the equation of the line, right? So I need both the slope, which I've got, and a point on the line. Well, when x equals 1, y equals f of 1, which is 1 over 1, or 1. So now I've got my point, right? The point 1 comma 1 is on the line. Now I got my equation. Just use the point slope formula. Y minus 1 equals minus 1 times x minus 1. Y minus 1 equals minus x plus 1. Y equals minus x plus 2. And that's it. That is the slope of the tangent line to that is the equation of the tangent line to f of x equals 1 over x at x equals 1. Okay, well, so now I want to find. Now I'm not even trying to find a specific value. I just want the function. Find f prime of x for this function. Okay, so let's use our definition again. The limit h approaches 0. F of x plus h, that's the square root of x plus h, minus f of x, that's the square root of x, over h. Okay, so I'm going to rationalize the numerator here. I'm going to multiply the top and bottom by the square root of x plus h plus the square root of x. Square root of x plus h, same thing in the denominator. Okay, so this is f prime of x. Let me get the label there. So this is the limit h approaches 0. Let's see, you multiply that numerator out. It's the square root of x plus h times the square root of x plus h, which is just x plus h. There is no middle term, right? Because I get minus square root of x times x plus 1 plus the square root of x times x plus 1 minus the square root of x times the square root of x. That's just x. All over h, square root of x plus h plus the square root of x. All right, so let's see. X minus x, that's just 0. Those cancel. So this is the limit h approaches 0 of h over h square root of x plus h plus the square root of x. The h's cancel, right? And that's nice because it was that got rid of the h in the denominator that was making it 0. Now I could just put 0 in there for h. And this is 1 over square root of x plus 0 plus the square root of x. Well, the square root of x plus 0 is the square root of x, and the square root of x plus the square root of x is 1 over 2 times the square root of x. And there's my answer, right? That is the derivative of this function. Okay, so that's how we use this definition. Right, fairly straightforward, but we've been sticking to pretty well-behaved functions so far. So that one of the next things we need to do is see how can we do this for more interesting, more complex functions. Before we do that, we do have a few more general things to talk about. I want to talk a little bit about how to tell when functions are not differentiable, because we saw in the last lecture that can happen sometimes. And I also want to talk a little bit about the relationship between differentiability and continuity.